And we have Martin Hira, who's a professor at Imperial College London, speaking about stochastic Yang-Mills. So over to you.
Okay, thanks a lot. Yeah, so thanks for the invite, well, the virtual invitation. Thanks to Hendrik and Andres for organizing this. Yeah, so most of what I'm going to talk about in that lecture series is one article which is on the archive, and there should be a link somewhere on the website, which is joint work with AJ Chandra, Ilyashevirev, and Hao Shen. And there's a second sort of follow-up article which is not yet finished, but then hopefully, you know, should be on the archive at some point before the end of the year or something like that. Now, probably most of you are not really familiar with Yang-Mills theory or Gage theories in general. And so today, what I wanted to do is to just, you know, try to give you some kind of introduction to Gage theories, explain what's sort of the philosophy, how these things came about and how these things get formulated, and, you know, what's the type of formalism that people use. And then tomorrow it's going to be a bit more probabilistic somehow. So towards the end of the lecture today, you'll see how there's a link to probability theory. So maybe I try first to just explain what Gage theories are about in general. So they're basically about describing symmetries. Okay, and so the kind of situation that you could have in mind is the following. So suppose that you have some sort of experimental setup. So you're sitting, well, so say you have different locations. So you have Hugo here in Geneva, and then you have Nicholas here in Berlin, and you have Roland here in Cambridge. And all three of them have, you know, some kind of experimental setup. They all have the same sort of setup. They can talk to each other over the phone and sort of compare their experiments and stuff. But imagine that their setup has some symmetry, right? So you have some kind of symmetry group here. So you have a group G, under which, if you want, their local universe is invariant, right? So you can imagine, for example, that whatever state space that they're exploring really looks like a sphere, but it's a sphere, you know, where you really can't tell where you are on the sphere if you move about, right? So every point on the sphere looks the same, but you know the points are distinct. So for example, you could have two of these states, so both of them are on a sphere, but they might not be on the same location of the sphere, and then you can maybe measure the angle between them, right? So you would have a reference point somewhere, and then you can measure the angle from that reference point. But the whole thing is completely invariant under rotations of the sphere, right? So your group G here would be just the, you know, three-dimensional rotations, for example. And well, if you just act on the whole setup with the group G, well, then your state would be rotated, but the reference point would be rotated as well. And so all the angles you measure would be the same. And so you really can't tell the difference, right? And well, then maybe, you know, Nicholas in Berlin has exactly the same sort of setup, right? And now what you want to do is you want to sort of compare what happens in Geneva with Hugo and what happens in Berlin with Nicholas. And of course, by them just talking over the phone, they have no way of comparing their states, right? Because the only thing they can do is they can compare their state to some sort of local reference state, but they have no way of telling whether the local reference state in Geneva is the same as the local reference state in Berlin or not, right? Since, you know, they're both sort of on a perfectly round sphere where you have just no idea where you are on the sphere, right? So now the only thing that they could do is, for example, Hugo could just, you know, go on a plane with his whole experimental setup and go and visit Nicholas in Berlin, right? And then when he does that, well, then now they're kind of sitting both in the same lab. So they can actually, for example, they could just compare their reference state and see if there's a non-zero angle between them or not, right? Or they could just use one of the two reference states to measure both states. And so now they can really compare their states. But in general, Hugo doesn't know, right? So since while he was on the plane, maybe, you know, all of his state actually was rotating while he was flying, right? He wouldn't be able to tell the difference, right? Since the whole thing is completely symmetric, right? So the only thing that he can know is that there's maybe, you know, some sort of group element G1 here that while he was flying from Geneva to Berlin was, you know, acting on all of his experimental setup. And then after he arrived in Berlin, then he was able to kind of compare with what Nicholas was seeing. And then same thing. So maybe now both of them might want to go and visit Roland in Cambridge, and, you know, same thing happens, right? So there would be maybe some group element G2 that while they're flying from Berlin to Cambridge would sort of act on their experimental setup. And then when they arrive in Cambridge, they can kind of compare their experiments to Roland's, and they can really compare the reference states, right? Now, what could happen is, well, so now they could actually close the loop. So they could go back from Cambridge, sort of back to Geneva, right? And now here's the interesting thing, is that in principle, well, in some sense, if everything was sort of flat in a way, right, then what you would expect is that by the time Hugo is back in Geneva, in a way, nothing has changed for him, right? But this doesn't have to be the case, right? So it might also be that actually in general, the composition of these group elements, sort of G1, G2, G3, might actually be different from the identity. Yeah? And Gage theory is really all about theories, setting up theories where this may happen. Okay. So in the discrete case, now the idea is that in the description of your sort of universe, well, whenever you go from one point to another, you would have to apply this kind of group element to your state. Right? But that group element might depend on how you go from that point to the other point, right? So the idea being that if you want to go from A to B, you really physically, so here space is really space, okay? So it wasn't just some sort of example or abstraction or something, right? So the space is really actual space or space-time. Okay? And the idea is if you want to go from a point A to a point B, you know, you have to actually take a path to go there, right? And depending on which path you take, you might end up in a different state by the time you end up in B, okay? And so if you want the like background state of the universe is something that precisely tells you how your state gets acted upon by this symmetry group as you move through space-time, okay? So in the discrete case, like the picture that I just drew, the idea is that, well, your space just consists of a number of discrete points. So here there are just 3 points corresponding to sort of Geneva, Berlin, and Cambridge. And for any 2 points, you have a group element. So that would be these G1, G2, G3 that tell you how your state changes when you go from one point to the other. Okay? But so now certainly one thing, right? So if say I call, maybe I call gamma xy right? Sort of the group element that corresponds to transport, say, from y to x. Okay, so the reason why I say y to x and not x to y is that, you know, composition kind of goes from right to left, right? And so with that sort of makes the indices more consistent. So for any 2 points, so if you want, you have like a grid or a graph with edges, okay, and the edges would be sort of between neighboring points. And if you want to go from anywhere to anywhere on the graph, you have to sort of follow these edges one by one. And whenever you go from a point vertex y to a vertex x along the edge that connects x to y, your internal state get acted upon by some group element, gamma xy, right? Now, one natural thing here is that, so the whole point here was to describe a situation where you have some kind of symmetry group, right, that does leave you the physics of the universe invariant. And that symmetry group is kind of local now, right? So what it says is that if you just look at what happens in Geneva, you can act with an element of your symmetry group, of that symmetry group, on what happens in Geneva, and nothing changes in the experiments you do in Geneva. And simultaneously in Berlin, you could act with a different element of your symmetry group on what happens in Berlin, and nothing would change to the experiments, right? So what you would want is that in general, if you have any function of space or of space-time with values in your symmetry group, you want the formalism to be such that if you act now with that function of space-time, nothing changes, right? And so what this tells you is that, so, you know, for example, how does this connection have to change, right? So these elements gamma xy, that's like a connection. So a connection is something that
Martin, you've frozen. Has he frozen for anyone else?
curve,
Yeah, for
it
me
gives
too.
you a notion of parallel transport.
Sorry,
right?
sorry, Martin, can you repeat that? Your
Yes.
connection froze.
Oh, yeah, so here the gamma xy's, right, they behave like a connection in the sense that they allow you to transport physical states from one point to another. Or it allows you to transport, if you want, the description of your physics from one point to another point, okay, from a point x to a point y, or y to x. And so it behaves similarly to a connection in differential geometry, where, you know, you can move tangent vectors along a curve. You get a notion of parallel transport along a curve, right? So it's somehow the same type of idea. And so now if you want, clearly, if you want invariance under that group G locally at every point, right, then that tells you how this connection should also transform, right? So in the sense that if I have a, so now your sort of Gage group, so the Gage group would be functions from space-time, so say RD, into some symmetry group G, okay? And that symmetry group G, in our case, we're always going to take this to be compact Lie group. Right, so you should really think of something like rotations in R3, or that type of symmetry group. Okay, so now if you have an element of the Gage group, so it means that every point in space-time you act with a symmetry, and you want this to have, in some sense, no effect overall. Right? Then what it tells you is that the gamma xy's, right, they should transform like gamma xy should be mapped to g of x, gamma xy, g of y inverse, right? Because you think of, if you have a state, right? So if you have a local state phi at some point x, right? And then the gamma xy, or say y actually, since gamma yx transports from y to x. Okay, so you have a local state located at y. And now what you want is that, transporting, acting with the symmetry group at y, and then transporting that state should be the same as first transporting the state and then acting with the symmetry group at x. Right? And so what this tells you is if you do the sort of global action of the Gage group, right, your connection should transform in precisely this way so that nothing changes, right? Because that tells you that if you first act on, so if you first act on phi with your Gage group, so you turn phi y into g of y applied to phi y, right? And then you transport it to x with the transformed connection, right? Then what does it do? So you have this guy here that acts on g of y applied to phi y, so the g of y's cancel out, and you see that that's exactly the same thing as simply first transporting phi of y to x with gamma, and then applying g of x, right? You see what I mean? So this way of transforming the connection is the only way which is compatible with the action of the Gage group on observables given by, transforming phi of y, say, into g of y applied to phi of y. Okay, so if you think of the phi as being the local physical state, which is symmetric under the action of this group G here, and so so that state would live in, some kind of vector space, and you have some representation of that group on that vector space, and so you have a notion of acting with a group element on that vector space. Then the idea is here that locally the physics described by phi of y is the same as the physics described by g of y, phi y, okay? But if I want to compare states, then I have to transport, right? So if I want to compare states that live in different locations, I have to transport them physically from one location to the other. And as I do this, they get acted upon with, this gamma xy. And now I want to say, well, the whole description should be invariant under this global symmetry, right, of the Gage group sort of acting independently at every point. And then that forces the Gage group to act on this connection in this way. Okay. So let me give you an example that, you might be familiar with. So that's sort of the canonical example to explain Gage theories, which is in a way classical and has nothing to do with particle physics. So the origin here of Gage theory, and Yang-Mills theory, so that was first proposed by Yang and Mills in 1954. And the origin is really particle physics, right? So the idea is that these states are at the very elementary level of particle physics. But it turns out that electrodynamics is also a Gage theory. Okay? In particular, if you sort of one situation in which you really see this is if you take one quantum mechanical particle, so no field theory, so it's just one particle, okay, that moves in a magnetic field. Okay. So the example here is a quantum mechanical particle moving in a magnetic field. So your magnetic field is B. And so how is that described? Well, so first what you do is you rewrite your magnetic field as the curl of a vector potential. Okay, so a magnetic field always has the property, so say there are no currents, no sources, so it has the property that the divergence is 0, so it's actually the curl of a vector field. So you write B equal to curl of A. And then your particle, so your particle is described by a wave function. So wave function psi, so that goes from, well, R, which is time, times R3, which is space, into the complex numbers. And the Schrödinger equation says that if I set h bar equal to 1, that I dt psi should be equal to minus I gradient minus electric charge times A square applied to psi. And then if you have an electric potential, there's another potential term. Okay, but let's just have no potential, purely a magnetic field. Then that's the Schrödinger equation. Okay. Now, in terms of physics, all the physics of the, if you want, the quantum mechanics is sort of invariant under changing the global phase. Okay, so if I take a wave function and I just multiply it by e to the I theta for any theta, there's absolutely no way of telling the difference, right? There's no experiment that you can make which actually tells the difference between the original wave function and the one where you just multiplied everything by e to the I theta for a constant theta. Okay. Now, if we sort of follow that philosophy of gauge theory, what it says is that, well, what we should think about is how the physics changes here if instead of just multiplying globally our wave function by, you know, a constant phase, we multiply it by a phase that's allowed to change in space, right? So that we take a different phase in one point, one region of space, than in some other region of space. And now, so consider.
Martin, sorry, what is G?
Yeah. Sorry?
What is G here in Schrödinger's equation?
What is?
G.
Oh, Q, that's the charge.
Ah, Q charge.
Yeah, so this here, that's just the electric charge. That's the way you interact with the magnetic field. Right, so I look at a transformation that maps psi into e to the I, say, chi of x times psi. Okay, so let me write, okay, so let me make it more precise what I mean. So let me just write psi equal to e to the I chi of x times psi hat. Now here, of course, I can always do that. You know, I haven't done anything. I've just done a change of notations. But now I can ask myself, you know, what kind of physics does psi hat obey? Okay. So if you look at the equation for psi hat, right, you notice that it's actually pretty much the same equation, except that what happens is that the minus I gradient gets turned into minus I, right? So minus I nabla basically gets turned into minus I nabla plus gradient chi. Right? So if you just write down the equation that psi hat obeys, would be exactly the same equation as before, except that the minus I nabla gets turned into minus I nabla plus gradient chi. But then you see that, well, this, we can actually undo this by changing A into A minus 1 over Q gradient chi. Right? So if I call this A hat, they just end up, you know, obeying exactly the same equation again. Now, what you also see is that the curl of a gradient is 0. So actually the magnetic field hasn't changed at all. Right? So I've just, so the describing the magnetic field here by a vector potential, there was some freedom here. Right? So even if I know what the magnetic field is, that doesn't uniquely determine what A is. Right? So I can find different A's so that the curl is equal to B. In particular, I can actually just add the gradient of a function. Right? So if I add the gradient of anything, I would still get the same B. Right? So here there was actually some freedom. And what I notice here is that actually changing the phase in a space-dependent way for my wave function is completely equivalent to simply changing, you know, the choice of A that I had, you know, where I kind of had to make an arbitrary choice in the first place anyway. So what you see here is that the physics actually doesn't change at all, or at least it appears not to change at all. So if I believe that the magnetic field is really the sort of physical measurable object, right? Then it appears that nothing has changed at all, actually. Right? If I believe that somehow, you know, you can actually measure the vector potential A, well, then something has changed, right? Because I had to actually change the A. Now, the interesting thing, so classically, we always think in electrodynamics that really the only thing that's observable is the magnetic field, well, magnetic field and electric field. And the potentials, we just think of them as some kind of, you know, trick or just some way of describing them, right? But not as something actually fundamental. We always think of the electric and magnetic field as being the fundamental thing. But here in electrodynamics, in quantum electrodynamics, it turns out that you can actually see an effect which, in some sense, classically does not make any sense. And so the setup is the following, right? And so that's called the Aharonov-Bohm effect. So the idea is that you want to somehow detect the effect of a magnetic field by a particle which is constrained to always move in regions where the magnetic field is actually 0. right? So in principle, if a particle moves in a region where the magnetic field is 0, it should just be completely unaffected by it. Okay, so that's what we think of it classically. But now think of the following situation. Okay, so you have a region here where you have some non-zero magnetic field, but you make the setup in such a way that this is really localized. Okay, so you think of so this is three-dimensional space, and think of it as sort of looking from above, and the lines of your magnetic field go somehow perpendicular to the plane of the board here. Okay, so there's this patch here where you have field lines that come in a way that's perpendicular to the patch, and outside of that patch B is 0. Okay, so here in the red region B is non-zero, and it points in the direction that's normal to the board, and outside of the red patch B is 0. Okay? And then take a beam splitter here, so that's a splitter, and you shoot particles in here, and you put 2 mirrors. So that's a mirror, that's a mirror. So now when it hits the beam splitter, the particle has sort of a 50% chance of going straight and a 50% chance of being reflected. But what the beam splitter does is it really turns that into sort of a quantum superposition. Right? So in a way, it simultaneously gets through and gets reflected, and you only tell which way it happened, by the time you measure things. But so it's in some sort of a Schrödinger cat type, superposition. So it simultaneously goes straight and gets reflected. So then the bit that goes straight, here it hits the mirror, then gets reflected by the mirror. And then the other one hits the other mirror, gets reflected by the other mirror. And then, by the time they get behind that region here, well, they both again end up sort of in the same location in space. Okay, and so then what you do here is you put some kind of detector. Right, so here you put some detector. And so now what you see in that detector, you should see some sort of interference pattern, right? Because the particle, so it gets split, they get recombined, the two trajectories are not exactly the same length, and so there's a slight phase shift in your particle, and then by the time you add it back up in the detector, well, depending on the phase shift, either this interference is sort of destructive or it's additive, right? So you actually see some kind of interference pattern in your detector. And now the interesting thing is what you do is you change the strength of that magnetic field in that red patch. Now, classically, you would think that should have absolutely no effect on anything in the setup, right? Because whatever the particle does, whether it goes straight or is reflected in the beam splitter, in any case, it never gets near the red patch where the magnetic field is non-zero, right? So in all situations, the particle would always be in a situation where the magnetic field, it's always only in regions of space where the magnetic field is 0. Okay, it never goes into any region of space where the magnetic field is non-zero. And so you would think that it would just not feel the magnetic field at all. But it turns out, and so this is really, an actual experiment that people did. So when you change the strength of the magnetic field, you do actually see a change in the interference pattern that you see in the detector. Okay. And the reason here is that, well, if you have some magnetic field in the middle, you cannot set A to 0 outside, right? Because A has to be a sort of smooth function with curl equal to your magnetic field. And now, you know, think of the extreme case where your magnetic field is basically like a delta function on a point, well, on a line, if you want, that points along the line. You can find, you know, you can find vector potentials so that the curl formally gives you that sort of delta function along the line, this kind of current, but they would not be zero outside, right? So they would be more like, you know, things, it's kind of like when you look at the logs. So what happens here is that even though the magnetic field is zero outside of the red region, here you have, so you have B equals 0, but A is non-zero, okay? And A has to be non-zero. And what happens now when you do your interference pattern here is essentially, you know, what you do is you end up sort of comparing the phase. So now what happens is, because of that equivalence between, you know, changing the vector potential and changing the phase. So here you end up accumulating, so the total amount of phase, so if you go around the whole setup once, you end up accumulating a phase which is given by, well, essentially the integral of that vector potential along a loop that goes around that experimental setup. And this then, just by Stokes' theorem, is just equal to the integral of the magnetic field inside. Okay. And so whatever you do, you cannot, you know, whichever way you choose your A, the integral of A along a loop that encloses your magnetic field will always be equal to the integral of the, you know, the magnetic flux inside that loop, just by Stokes' theorem. Right? And what this calculation here tells you, it precisely tells you that if you, you know, sort of compare the phase that you pick up along the two possible trajectories, well, there is one contribution that comes from the fact that you actually move in space. And so, you know, the phase actually changes as you move just because of the momentum of the particle. But then there's the additional contribution that comes from the vector potential. And if you look at the difference between these two contributions, that precisely corresponds to just the line integral of A along, you know, along this trajectory here, which cannot be zero, right? Which has to be equal to the magnetic flux. Okay, so that's a situation where you really see there's a sort of real world effect, if you want, of this situation where even though you have a symmetry, when you move around and you get back to the same place that you started from, because, so here in this case, because you've sort of enclosed a region where you have this magnetic flux, by the time you come back to your starting point, your state has actually changed. The description of your state has actually changed. Okay. So, okay, so now let's try to set these things up in the continuum, right? So at the very beginning, I mentioned that the sort of natural, so, you know, it's somehow in a way relatively easy to think of this situation in the case where space is discrete, right? So say all of space is just like a graph, and then for every edge of the graph, you give yourself, you know, something like a group element in that group G. and that group element tells you how states change as they move from one point to another in that graph. So now let's try to take some kind of continuum limit of this. Okay, so you want to take some continuum limit. So what this means, if we think of this grid as being very, very fine, right? So think of the space as being still discrete, but with a tiny grid size, and then think of all these group elements as being very close to the identity if you move by a tiny amount, right? So that's somehow a reasonable thing to assume. So you say, okay, so if we move by just a tiny amount epsilon, then the corresponding group element should be, so if I take, say, the gamma between, say, x and x plus epsilon ei, right? So let's say I take a regular grid, and so I have my basis vectors ei that just correspond to the unit directions in my space or my space-time. And so if I just move by one step in my grid, I want that change to be very close to the identity. And so I write it as the exponential of some element in the Lie algebra. And I want this to be also of order epsilon, right? So I think of this as being e to the epsilon ai. And then, I want the ai's then in the limit to become kind of fields or functions of space. And so the natural space point to associate to ai, right? So since it kind of, this is like, it lives on an edge in the graph, right? Because it tells you what happens when you move from the point x to the point x plus epsilon ei. So the natural space point to associate to this piece of data is the one that's halfway along the edge, right? So halfway along the edge, I would be at x plus epsilon over 2 ei. Okay. So
Martin, there's another
Yep.
2 minutes before we take a break. Is this a natural place to stop, or?
Yeah, this might be a good place to stop.
And we can start a few minutes.
Okay, yeah.
Okay.
That sounds good. Okay, so let's do the 15 minutes break now then.
Should we have some questions? Sorry, should we have some questions? Yeah.
Sure, yeah. Oh, you're asking me.
No, sorry, sorry, but so that people should ask questions. So that experiment is actually, I mean, it's an actual experiment that people in physics classes learn about.
Experiment. Yeah, it's an actual experiment. So I think the effect was sort of predicted, I think sometime in the early 60s or something like that. Mm-hmm. Or maybe even earlier, or maybe the experiment was done in the early 60s, something like that. Yeah.
Okay. So now there's a question in the chat. This is, yeah, you can perhaps see it.
Oh yeah, for these gamma, do we only allow increments in the form of these small steps? Right, yeah, so you have to fix a graph, right? So of course here, okay, the choice of somehow, making the graph like a regular square grid is completely arbitrary, right? I mean, I suppose that you could have chosen a different grid or different kind of lattice. And then it's sort of up to you to decide, which edges you connect and which edges you don't. But okay, I mean, the square lattice is just very natural in order to, derive the continuum versions that, we're actually going to work with later on. Yes. Yeah. So at the discrete level, you give yourself, for every edge, you give yourself a gamma that, corresponds to it. So in a way, it's for every oriented edge, but then the convention would just be, if you change the orientation, you just take the inverse. Okay, so if you go along an edge and then you go back exactly the same way as you went, then you want nothing to change. Okay, so crossing an edge and then going backwards along the same edge, the composition would be the identity. And then if you want to go somewhere else, then you have to decide which way you go, right? So you just follow a number of edges, and then, the group element that describes that would just be the, you just multiply all of these gammas along your path. Is it really important to, oh, well, you see, so it wouldn't be very natural to write AI of X because of that thing, right? So if I write gamma of X plus epsilon EI X, right, because of what I just said, this guy should be equal to the inverse of the previous one, right? And so with this way of writing, this is exponential minus epsilon AI of, again, X plus epsilon over 2 EI, right? Whereas if you wrote here an AI of, so if here you wrote AI of X, then it means here you would also have to have AI of X, but then that would not be very consistent, right? So then the notation would not be consistent. Because here the AI of X, the X is sort of the first argument, whereas here the X is the second argument. I mean, of course, you could do that. It's purely a matter of notation, but somehow the notation is much more natural if you put it halfway.
So here AI are just real numbers, right?
No, so here the AIs would be, so in general, right? So these guys belong to some Lie group G.
Mm-hmm.
And so the AIs would be in the Lie algebra for G, right? And so the exponential is the exponential map in the Lie group, right? That turns the Lie algebra into a group element.
Okay.
Yeah. And so if these are matrices, then it's really just the exponential in terms of matrix, right? So you can think of this as being an orthogonal matrix. So if this is an element of SON, for example, then this guy would be an antisymmetric matrix.
Okay.
Right? And then this would just be the matrix exponential.
And for concreteness, in the case of, oh, okay, sorry, I think someone's asking exactly what I wanted to ask.
Okay, does it make sense to think about as there being one degree of freedom in the phase shift, and then you have to respect unitarianism? Yeah, I guess. Yeah. Okay. Any other question? Okay, so the AIs, okay, so the Gage group, so let's just in terms of terminology. So the group G, that one, people call it the structure group here. And then the Gage group would be functions with values in G. Okay, so like at every point of space, you give yourself an element of G. Okay, so the Gage group would be some sort of curly G, and that element of curly G is just a function from space-time into the group G. And the A's here, they take values in the Lie algebra of G. Okay, so that G is just a finite dimensional Lie group. think of it as just being a subgroup of SON also, because I always want them compact. So then this would just be a skew-symmetric matrix. Okay, so the AIs now would be functions on your space-time or your space with values in the Lie algebra, and the Lie algebra would be maybe some subspace of some skew-symmetric matrices. Yeah, so now let's try, so the aim now is to try to just guess, if you want, what is the natural continuum setup that corresponds to the discrete setup that we just described, right? So the discrete setup is the one where you have a graph for every edge on the graph, every oriented edge of the graph corresponds to an element of that structure group G, and G is just a compact Lie group. And then you have a natural way under which these things transform under the action of the Gage group, where the Gage group is all the functions from the vertices of the graph with values in the structure group, right? And if you have such an element, so that would be, such a function, little g, that goes from vertices of the graph into elements of the structure group G, then under such functions, the natural way for these gammas that you associate to every edge to transform is that one, right? And if you transform in this way, then, for example, also if you move along any path in the graph, right? So if you go from one point x1 to a point xn, by going first from x1 to x2, then x2 to x3, and so on, then the group element corresponding to that is the multiplication of all the gammas for all of the edges that you traverse. And then if you look at this expression, what happens under the action of the Gage group is that all the intermediate factors of gamma, they all cancel out. So it's like a sort of telescopic product, if you want. And the only thing that's left is sort of a G of the starting point times all the product of the gammas that you traverse times G at the end point, inverse, right? So you have the same kind of expression if instead of looking at one edge, you look at any number of edges that you traverse, right? And so let's see now what's the natural continuum version of this, right? So we've already seen that. So the idea is to just discretize space. I just take a square grid. And I assume that everything, the grid size is very small, and everything varies smoothly at the larger scale. Okay? And so the gammas now are naturally described by these AIs that now take values in the Lie algebra rather than the Lie group. Okay? And you see the AIs, so at every point, well, you want one of the AIs per direction, right? And it's really per oriented direction. Okay, so if you look at the AI that corresponds to going up, it's equal to minus the AI corresponding to going down, right, as we've seen here, right? So that comes from the fact that the gammas associated to one oriented edge are the inverse of the gammas associated to the same edge with the opposite orientation, okay? So that at the level of the A's, that tells us that if we look at the A, if you want going up at one point, it's minus the same A going down. And so if you want, what this really means in the continuum is that the A's are really a one form, right? So at every point, you give yourself a direction and it spits out, well, not a number, but an element in that Lie algebra. Okay, so it's a one form, except that it's not a real valued one form. It's a Lie algebra valued one form, right? So the A is a G valued one form. So that's, if you want, the natural A, the natural continuum object that corresponds to the gamma xy's that we had at the discrete level. Now, the first question is now, how does it behave under the action of the Gage group? Right? So if I take a element of the Gage group, that would be a group valued function. And I'm on purpose vague in terms of, so there's no analysis here at the moment. Okay, so I'm vague in terms of regular, what exactly do you mean by regularity? How regular do you want these things to be, etc. Okay. So for the moment, we just assume that everything is as smooth as you want or as smooth as you need. So now, what is the natural way for A to transform under the action of G? Right? Well, we've seen how the gammas transform, right? And so now we just want to, make epsilon very small, do some kind of first or second order expansion, and see what this tells us about the A's. Okay. So we look as before. So let's just look at one edge. Okay, so we just look at one edge where we have X here, and we have X plus epsilon EI, and we just look at what happens along that edge. And the G, since G is supposed to be a smooth function, that means that the value of G at the point of the little g at this point here should be very close to the value at this point here, right? So there should be an expansion in powers of epsilon. And so in particular, it tells me that I can write, say, G of X plus epsilon EI in the form exponential of epsilon and then some BI, say, of, again, X plus epsilon EI over 2 times G of X. Right? So two elements that are very close in the group G, well, it means that they differ by something which is very close to the identity. And if it's very close to the identity, I can write it as the exponential of something very small in the Lie algebra. Right? So I'll write it as an exponential epsilon B. And again, the B, that one belongs to the Lie algebra. Now at the continuum level, what does this mean, right? So it really means that Bi is equal to the partial derivative of the function G times G inverse, right? So if you think of G as being taking values in a matrix group, then this is really what it means. So now how do the A's transform? Right, so we've seen that under the action of the Gage group, you want the gammas to transform like, right, so we wanted gamma xy to transform like G of X, gamma xy, G of Y inverse. Right? Now, gamma xy, if y is, I take for y x plus epsilon EI, then this is approximately e to the epsilon AI of, well, always x plus epsilon EI over 2. right? And so I want this to transform into, well, g of x times the gamma xy, which is epsilon ai da da da. And then g of y inverse, but g of y is this guy here. And so the inverse of this guy is g of x inverse times the inverse of that factor, which is just e to the minus epsilon bi of blah, 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 right? Now, this I can write it as, well, conjugation, if you want, sort of commutes with exponentiation, in the sense that there is an action of the Gage group, of the Lie group onto the Lie algebra, which is called the adjoint action, which is such that this is just e to the epsilon adjoint action on ei, on ai of blah, 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 right, times e to the minus epsilon. And then by Baker-Campbell-Hausdorff, I can actually, the exponential of a times exponential b is exponential of a plus b times, and then there's, you know, additional terms, but the additional terms are higher order, right? So if these things are all order epsilon, then I get, here I get the bi, and then I would have an order epsilon square, right? And so what does it tell me? So it tells me that the a, right? So what does it show? So it shows that a, so a of x, say, transforms by pointwise conjugation with g, but then minus this b, and the b was just the dg times g inverse. Okay. So now the natural analog of the gammas is a
has anyone else lost connection?
I've lost Martin, yeah.
Yeah. Okay, maybe wait.
That's not good.
on that connection.
Martin, you froze.
Is
We lost the last. Are you still frozen?
Here. Yes. Hello.
Yeah, you froze for the last 2 minutes. Or last minute, 30 seconds.
And again.
And again.
It works now?
Your video is frozen, but I just heard you.
I don't really hear you. I hear you very badly.
Can you hear me better now? Because your video has come back.
Yeah.
Okay, so we lost you for a minute and a half.
Oh, I see. Oh, that's bad. Sorry about that.
No worries.
Okay. Yeah, so what I was saying is that what this little calculation shows is that the analog of the gammas is a one form with values in the Lie algebra. The analog of the Gage group is again G-valued functions, but now it's smooth functions, you know, on the continuum space. And the analog of the action, so at the discrete level, we had that action here. And the analog of this action at the continuum level, what this little calculation shows us is it's this action here. So it's not just that we do a sort of pointwise conjugation with the Gage group, but we do a pointwise conjugation, and then there's this extra term, this minus dg times g inverse. Right? So this came from the presence of this term here. Okay. So in general, now we also have a notion of what's called the covariant derivative. And so that's the natural thing. So a covariant derivative so the idea is now if I have a physical state, right? So then that would be an element. So I have a function phi that goes from my space, say Rd, with values in some vector space, say V, and that space V comes with an action of G, right? And the idea being, again, that the physics encoded by that state is invariant under the action of G. And so now if you have this, well, we've seen that there's a natural way now to transport states from a point to another point. And so if we're given a field, so we're given a point at every state, a state at every point, there's a natural differentiation operation which corresponds to not the usual differentiation, right? So in principle here, the phi takes values in a vector space, so I can just differentiate, right? So it's a linear space, so I can just take derivatives. But that wouldn't be the natural thing to do, because then I'm kind of comparing apples and oranges, right? Because if I take a derivative, it's really a limit of a finite difference. And so I'm comparing the state at one point in space to the state at another point in space. And we've seen that the whole philosophy of these Gage theories is that you shouldn't do that. So the only thing you can compare is states at the same point in space. And so if you want to compare them at different points, you have to transport them first from one point to the other, right? But if the points are very, very close to each other, then it doesn't really matter how you transport, right? You just transport along a straight line. And so the natural way of, right, so the natural sort of derivative of phi, right, so this would be a derivative with respect to the A guy, well, at a point X, the idea is that, well, you take phi at X plus epsilon EI, but then you transport it to X with your gamma, and then you compare it to phi of X, and then you divide by epsilon, and you take the limit as epsilon goes to 0, right? So that's somehow the natural way of taking a derivative in this context. And now if we check what this is, right? So this is really 1 over epsilon times e to the epsilon AI of, well, say there's x plus epsilon over 2 AI, but then that's, here I don't care because that would be an order epsilon squared term, times phi of x plus epsilon AI minus phi of x. But then I just do a Taylor expansion, and so I just see that this is phi of x plus epsilon AI minus phi of x plus epsilon AI of x acting on phi of, well, say x plus epsilon AI. Right? But then now this is nothing but the usual directional derivative of phi for the first term. And in the second term, you see the epsilons just cancel out. And then the fact that the points were evaluated at sort of epsilon away, since everything is smooth, that's just something of order epsilon, which drops in the limit. Right? So what we see here is we have an AI of X acting on the phi of X. Right, so that gives you a natural notion of derivative, which is the notion of derivative that transforms in the correct way under these Gage transformations, right? Whereas the usual partial derivative doesn't transform in the correct way. Okay, so now we've seen what's the natural analog of the gammas. We've seen the natural analog of the G's. We've seen how they transform, and we've also seen that once you have such a connection A, you get this natural notion of covariant derivative, which is notion of differentiation that behaves correctly under Gage transformation. And so now the last continuum object that I wanted to introduce is what's called the curvature. And so that's a very important object, which tells you to what extent your state actually changes when you go along a little loop and get back to your starting point, right? So if you have a state and you transport it along a loop, a closed loop, then you can actually compare it to the initial state, right? Because you're back to in the same location in space. And then you can ask yourself, by how much has it actually changed? Right? Now, if I move my state if I take a little loop of sort of diameter epsilon, right, what do I expect by how much it changes? Well, to first order, well, if I move by about epsilon, I'm going to change by about epsilon, right, since everything is smooth. But then if I move by epsilon in one direction and then I move by the same amount back, then I don't change at all. So that just cancels out. But if I move sideways in between, then it doesn't cancel out exactly, right? But it still cancels out to first order. And so what I would expect is that by doing a little loop of diameter epsilon, the change that I see would be of order epsilon square. So I expect the order epsilon contributions to just cancel out. But then there would be some kind of epsilon square contribution that's left. Okay, and epsilon square is just the area of the little loop. And so in general, you expect, as you go around a little loop, your state to change by an amount that's about roughly proportional to the area of the loop. And then the proportionality that you get, that's called the curvature of your connection. Okay. And now this depends, of course, on the orientation of your loop. Okay. And so to describe the orientation of a little loop, well, basically I need to give you two vectors, right? Because somehow the simplest loops that I can build are just like little squares. Okay, if I think again of my space as being discretized with kind of a square grid, then the most elementary loops that I have are just little squares. But to determine a little square around every point, well, I have to give myself two directions now, instead of giving myself one direction, right? So, and this, by the way, is exactly, so it's called curvature here in this context. Of course, there's a notion of curvature that you all know from differential geometry, but they're really the same. Okay, so in the sense that the Riemannian curvature tensor, one way of interpreting it is precisely by saying, well, you know, the Riemannian curvature tensor is this sort of crazy, scary object with four indices, right? But so what do the four indices really correspond to? Two of the indices are the ones that correspond to your little loop, okay? And then on every little loop, that tensor tells you how tangent vectors get changed as you transport them along the loop, right? So you take a tangent vector, and you transport it, you parallel transport it along the loop, and you get back to where you started from, but your vector has changed. It's changed by order epsilon square. And now that gives you a linear map that maps tangent vectors to tangent vectors. So that's again an object with two indices, one upstairs and one downstairs, because it's a map from tangent space to tangent space. And so the full Riemannian curvature tensor is precisely the object that describes that, right? So it has to have four indices because there's two indices that tell you which loop you're considering. And then there's one index for the direction of the tangent vector that you're moving around. And then the last index is the one that tells you in which direction it actually moves. Okay, so it's natural that you end up with a thing with four indices in the differential geometry case. Here, we just end up with something with two indices with values, again, in the Lie algebra, right? Because we take a little loop. So that's two indices that tell us in which direction how our loop is oriented. And then we move along the little loop. We say, well, the amount by which the gammas, when I add up the gammas along the loop, by how much do I change? So how much do I differ from the identity? I differ by a very small amount. So to describe it, that's going to be an element of the Lie algebra. Right? And so the natural object here for the curvature is a two form with values in the Lie algebra. Okay. So the curvature, which is usually called F. So now it's a guy with two indices. And the two indices really correspond to, right? So I have a point X. So that's my Fij of X. And now the two indices, they give me two elementary direction. Right? So I have an I and a J. I'll say EI and EJ. And now what I do is I move like that. Okay, so I perform a little loop. So what I'm going to do is I'm going to just move along that square and compute what's the order epsilon square contribution of that little motion. Okay. And then I postulate that, well, there's always factors 2 or something here, right? So I postulate that the contribution of this should be of order exponential of 2 epsilon square times Fij of X. Okay, and that's my definition of the Fij. And that guy now is again going to be an element of the Lie algebra. Okay. So let's try to derive an expression of the Fij from the A's, right? So it's the A's tell us how things get changed as we transport them from one point to another. And so now I just have to multiply all the contributions along the loop. Right, so this guy would be about what? Well, so there's the first bit is I go down by Ej, so I have an e to the minus, so it's a minus because I'm going from x to x plus epsilon Ej, whereas the plus was the one that was actually going backwards from x plus Ej to x. Okay. So here I have a minus epsilon Aj of x plus epsilon over 2 Ej. So that's the first bit of contribution, right? So that one. Now the second bit of contribution is this one here. And so that's now e to the minus ai, but now it's at x plus epsilon Ej plus epsilon over 2 ei. and then I'm going up again. So now I have a plus epsilon aj again. This time I'm one step to the right, so I have a plus epsilon ei plus epsilon over 2ej. And then finally I go back, and so I have an epsilon ai at x plus epsilon over 2 ei. Okay. And so now you see to order epsilon, and there's an epsilon missing somewhere. So to first order, when I multiply exponentials, the exponents just add up. And so you see to first order, this guy cancels out with that guy, and this guy cancels out with that guy. I just get 0, right? At order epsilon, I just get 0. But I have a non-zero contribution at order epsilon square. And so I have to now figure out what's in the exponential at order epsilon square. And so I just use Baker-Campbell-Hausdorff. So let me just remind you that Baker-Campbell-Hausdorff tells me that at second order, exponential a times exponential b is about exponential a plus b plus 1/2 bracket between a and b. Okay, so that's, and then there's higher order terms. Okay, but I only need to look at second order. Okay, so if I apply Baker-Campbell-Hausdorff to the first two guys here, right, that tells me that this is about e to the epsilon, the first ai here, plus that aj, and then I have an epsilon square over 2 bracket of ai with aj. And then same thing for the other two. So I have a minus epsilon ai minus epsilon aj, and then plus, because it's minus times minus, plus epsilon square over 2, and again bracket ai aj. And now I have to again multiply these two guys, but at this level, I actually only need to add them up, because what you see is that if I take the bracket, so first I only care about epsilon square terms, right? So I don't care about epsilon cube or 4. So I really only need to look at the bracket possibly between this guy here and this guy here. But these are sent to first order, they are the same guy. They are both epsilon ai plus aj. Now, of course, they are not quite the same guy because they're not evaluated at the same location. But then that difference would be an order epsilon square. And therefore, by the time you multiply them, would be an order epsilon cube. And so I don't care about it. Okay. And so here, I really just need to add up the exponents. And so if I add up the exponents, what do I get? So I have this bracket, which just give me an epsilon square ai aj. And then I have all the a's. So of course, to first order, they just cancel out. But then since the point at which they evaluated, that point changes by order epsilon. And so there's an order epsilon square contribution from the first order Taylor expansion, which I can't drop. Okay, so the epsilon square term here corresponds to, well, you know, if I look at, for example, this guy minus this guy here, this is actually just the derivative of the ai guy in the jth direction, right? Maybe with a minus sign. and this guy minus this guy here is just a directional derivative of the AJ guy in the I direction, right, with a plus sign here. Okay, so what I get here is a plus directional derivative of the AJ in the direction I minus directional derivative of AI in the direction J. Okay, so this is again epsilon square. Okay, and then everything else is order epsilon cube or higher. So what I see is that, therefore, so if I just identify things, I see that my Fij, oh, actually write it intrinsic. Oh, okay, so let's write Fij of x is, well, so there's a half. So it's a half di aj minus dj ai plus a half ai aj. And so if I think of these as being forms, then what you can actually see is that this can be written in a sort of fancier way as well. The first term is actually a exterior derivative. So this is actually just the exterior derivative of the one form A, which gives you now a two form F. And then the second term is some sort of a mix between the Lie bracket and the wedge product. Right? So if these guys were scalar, then having just AIAJ would simply be, well, AIAJ minus AJAI divided by 2 would be the wedge product. And then here, well, these guys actually take values in the Lie algebra. So you simultaneously take the bracket, and the bracket has the correct antisymmetry. So this I can write it as a half of, sometimes this is written like this, right, to show that this is, in some sense, it's like the wedge product, but where products are replaced by Lie brackets. Okay. So, okay, so we have now this curvature, and the curvature, so the curvature at a point, remember that corresponds to by how much, right? So what's the action of the gammas of your connection on transporting your state along a little loop right near that point, right? So in particular, it really corresponds to, so this is, right, so the difference between the A's, so the A is transformed in a somewhat complicated way under the Gage group. Remember the way they transformed here was just by the adjoint, but then minus this additional term. And this really came from the fact that the A's connect 2 points that are not at the same location, right? And then we had to actually transport one point to the other one, and that gave rise to this term here, which in the end turned into that term here. F here is just transporting around a little loop. And so if I act on that guy with the Gage group, then it just acts in the natural way, which is simply by conjugation, right? Because the F corresponds to transporting back around the loop back to the same point. And so when I act with my Gage group at the point X, well, the starting point of the loop gives you a multiplication by g of x, and the endpoint gives you a multiplication with g of x inverse, but it's really the same x here. Okay, so the action of the Gage group, say curly G on the curvature, is simply that your Fij of x just gets turned into a G of x, Fij of x, G of x inverse, or if you want, add. Okay, so here you don't have this additional term, and that comes from the fact that this F really corresponds to what happens along an infinitesimal loop rather than an infinitesimal line. Okay, okay. And so now in the last 5, is there a, oh yeah, well, yes, that epsilon.
I think you can take an extra few minutes because of the technical difficulties.
Yeah, yeah, it's okay. Actually, I only need 5 minutes. So what we have now is we have all the objects that we need in order to formulate the Yang-Mills theory. So in Yang-Mills, or in pure Yang-Mills, so pure Yang-Mills, if you want, corresponds to the situation where you only care about the connection, and in some sense there's no physical state. Okay, so in a way there are only symmetries, but there's actually no state that the symmetries act on. But then you can add a state to it, and we'll see in a second how that works. It's very easy. But the pure Yang-Mills is an action just for the connection A. Okay? So your state, if you want, so say Yang-Mills. So now my state is this one form A, but which really, it's really a connection rather than a one form, right? Because it transforms in this slightly weird way with this additional term. With values in the Lie algebra G for some fixed. So the Lie group G is fixed once and for all. Okay, so the capital G. And then the energy, or the action, is given by 1/2 integral over your state, over your space, say sum over I and j of your Fij of x square dx. Okay. And remember so that's the curvature, right? So this guy depends on A, of course, right? So the F is a function of A given by this formula here. So your state, if you want, is your connection A. And then the curvature is computed from A in this way. And then your action is just the L2 norm, if you want, of the curvature, where here you have to, right? So you have to say what this norm is. So this is a norm on the Lie algebra, and it's basically, well, up to scalar multiple, there's only one norm on the Lie algebra, which is invariant under conjugation. Okay, so this is the unique, well, okay, unique in quotation marks because it's unique up to scalar multiple. Okay, but it's the unique norm on the Lie algebra such that the norm of add GH is equal to the norm of H for every H in the algebra and for every G in G. Okay, and it turns out that, so that's a theorem that if you have a compact Lie group, then there is such a norm and it's unique. Okay? So that's sort of the natural norm, a natural norm that you would put on your Lie algebra, and then you just take the L2 norm of your curvature. Now, the nice thing about this action is that first you see, since the curvature transforms, the curvature transforms in this way here, right? So pointwise, it transforms on the Gage group just by conjugation. Then because of this property here, that tells you that the action doesn't change under the Gage group, right? So if I act with my Gage group on the curvature here, the action stays the same. And it stays the same, the integral is the same just because the integrand is the same, right? It really stays the same pointwise somehow, not just globally once you integrate it out. Okay. And that's what you want, right? So that's the thing you want, because we wanted some theory which is invariant under the action of the Gage group, right? So the Gage group is supposed to be a symmetry. And so you wouldn't want the action to actually change when you act on it with the Gage group. Okay, so you see that, so the properties here is first, it's invariant under the action of the Gage group. And there's actually a second property, which is that, and that's actually the same, it's the same property as what phi-4 has. Okay, so we've seen in Hugo's lecture that in 4 dimensions, the phi-4 action is scale invariant. Right? So if you rescale the phi-4 action, so gradient phi squared plus phi to the 4, if you rescale it, at least formally, you get exactly the same, or it just gets multiplied by something, right? But the two terms, the ratio between the two terms stays the same in 4 dimensions, right? And in dimensions, if you're in dimension 3, then, or lower than 4, then in some sense the gradient phi term dominates, and if you're in dimension higher, then it's the phi-4 term that dominates when you rescale. That Yang-Mills action has exactly the same property, okay? And you kind of see that because formally it looks really very much like the phi-4 in a way in terms of homogeneity, right? Because the f, there's one term which is like a derivative of a, and then there's a term which is quadratic in a, right? But then it gets squared and integrated over, right? So by the time you square it, you have one term which is like a derivative squared and one term which is like an a to the 4, and then there's a mixed term. Okay, so in terms of scaling, it actually behaves like phi-4. Which means that in 4 dimensions, it's scale invariant. So it's scale invariant in D equal to 4. Okay. And here, if you want the conjecture, and there's, you know, if you can prove that conjecture, you're probably quite a long way on the way to cashing in the $1 million clay problem for Yang-Mills. So that conjecture would be that in 4 dimensions, unlike in the case of phi-4, that Yang-Mills theory is non-trivial. So you do actually have sort of like a non-trivial scaling limit. But we're not going to talk about 2-dimension. Okay, but that's sort of the 2 nice properties of this. And it turns out that this is the only expression that you can write down which has these 2 properties. Okay, and so it's a very, very natural kind of action to look at. And so the goal here, well, if you want the ultimate goal, which we haven't reached, would be to be able to give a meaning of the measure corresponding to that action. So to some measure that formally you can argue corresponds to e to the minus that action. In dimensions 2 and 3. Yeah. Well, ideally you'd want to do it in dimension 4 also, but that is expected to be even much, much harder. But that's sort of the direction that that's sort of, the kind of goal that we want to see in the distance. Okay, and so that's what we're kind of trying to move towards. Okay, but I think, I'm sort of running over time, so I should stop here.
Okay.
So that's it for today, and see you tomorrow.
Okay, thanks. So let me unmute, or at least allow everyone to unmute. Yeah, everyone can unmute now, and then we can give Martin a round of applause. So are there any questions?
So Martin, what do you mean that the actions are invariant under G? Because sort of the way that the norm is defined, isn't it giving you that it's invariant under G automatically? Yeah.
So these two properties are trivial to see. So I'm not saying that this is something difficult to see. Yeah, so this is defined in such a way that, that's right. The way the norm is defined, it immediately tells you that this is invariant under G. But this is the Gage group, right? So this is not, okay, G, this G is different from this, right? So this G is the one where your group element is allowed to depend on X as well. Okay, so it's not just the global, okay? So it's not just an element of the Lie group G, it's a function with values in the Lie group. Okay, but the way in which it acts on the curvature is simply by pointwise conjugation, right? So that's what we've seen here. And therefore, as you say, it's sort of trivial that this quantity is invariant, because simply at every point X, this quantity here is invariant under this action here.
Any other questions? So there's a question in the chat.
Yeah, we assumed our G to be invertible in terms of PD's physical property, and could also formulate desired properties and processes. Not sure what you mean. So here, here everything takes values in this Gage group. So sort of like by definition, everything is invertible because it's a group. So I don't think that this whole business would make much sense, right? Because inverses show up everywhere, right? The way the Gage group acts on the gammas at the very beginning at the level of the lattice. So even what we discussed at the very beginning at the level of the lattice wouldn't really make sense if the capital G wasn't a group. So I don't think this has much to do with reversibility, by the way. So this is not. Yes, Milton.
Hi. So I was wondering, you assume that the Gage group G is compact because abelian groups are boring, or there's another?
Well, abelian is fine, right? U1 is compact also. So you can have, right?
Yeah,
but they would have to be copies of the circle rather than the line. Yeah. Yeah, because if it's not compact, then you're sort of there are various places where things go wrong somehow if you're not compact. So for example, in general, it wouldn't be true that you have a norm which is invariant under the under conjugation, right? So yeah, so you kind of want compact.
Okay.
Bi-invariance would be okay for compact type, which includes all abelian groups. So
okay, maybe, yeah.
Bi-invariance.
But the thing is that at the end of the day, so Yang-Mills is used to describe. So, for example, the standard model is Yang-Mills coupled to a whole bunch of matter fields. and the Yang-Mills is, you know, so the Gage group there is, I don't remember exactly what it is, but it's, you know, SU2 times U1 times something. So it is sort of like the most interesting case, if you want, is a relatively simple sort of compact Lie group of rather finite dimension. Yes, Henri.
Yes, I have a question, Martin. If you are in 4 dimensions, you look at space-time. So should you change the norm to take into account the fact that you are on a Minkowski space, or, I mean, how would you, what would be the physically relevant entity?
Yes, yes, you're right. Yeah, yeah. So you would have to, that's correct. Yeah, so if you want to do the correct sort of relativistic one, then you would have to do these things in Minkowski space. Yeah.
I see. Okay, thank you.
All right, so if there are no more, I mean, are there any more questions? Okay, so let's give Martin one last round of applause, and then it's British tea time. So, yeah. So feel free to unmute yourself. And okay, so see you all at 3:15 for the next talk.